Welcome, everyone. My name is Greg Risselman from Olympus NDT. I'd like to welcome everyone to the second installment of our webinar series, Introduction to Phased Array Inspection using the OmniScan MX2. This series is designed to take the participant through the basics of preparing a single group phased array inspection using the OmniScan MX2. Today's installment is part 2 of the series and will cover sector scan basics and introduction to the data views and displays commonly used in automated UT and phased array. Our presenter today is Chris Magruder. Chris is the Phased Array AUT Manager for Olympus and has been developing and delivering phased array systems for over 12 years. The webinar is budgeted for about 60 minutes. The main presentation should last approximately 45 or 50 minutes, leaving 10 or 15 for questions. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. Do not type your questions in the chat panel, as we do not monitor the chat for Q&A. If we don't get to your questions during this live webinar, they will be addressed personally either by email or by phone after the event is over. Now, without further ado, I'd like to turn the presentation over to Chris Magruder. Chris, it's all yours.
Good morning, afternoon, or evening, everybody. Thanks for joining us. Again, this is part 2 of our continuing introduction to phased array using the OmniScan MX2. The supporting material used for this webinar included in the downloads that you're going to receive are the complete PowerPoints, and most of the material is also available in the training material manuals and books that you see here available on the Olympus website. About a month ago, in part 1, we discussed probe parameters, wedge parameters, materials, and a focal law beam formation, the fundamentals of phased array. Regardless of the instrument or the manufacturer, all calculators and instruments basically require these 4 groups of information: 3 parts hardware, 1 part software to generate the focal laws. We had talked also about probes and wedges, and for the MX2, the overwhelming majority of these applications are limited to 1D linear array probes like you see circled here. And the majority of these are 1D linear flat arrays, which we'll be using today. All of the software updates for the instrument can be found on the Olympus webpage. You're going to be seeing a little bit newer version of the software today if you have not updated your software recently. We would encourage you to read the release notes and keep your software updated as new features and bugs are being fixed pretty regularly. So in today, as we're going to start using the instrument and forming some sector scans and starting to learn the ABCs of manipulating the MX2 sector scan, we need to talk a little bit about the hardware. The MX2 is a modular instrument, meaning that you can purchase different modules that differ in both the number of UT channels and the configuration of the phased array channels and multiplexer. The 2 newest versions of the OmniScan line of modules are the UT2 2-channel with designed for improved TOFT, and the latest PA2 modules that allow both phased array and conventional probes, including TOFT, to be used simultaneously, whereas the older generation, it was one or the other in acquisition mode. So the modules will secure to the back of the instrument, and based on the configuration will limit your ability. And the different modules come with a different voltage, different pulsar and multiplexer configuration depending on the needs of the customer. Using the MX2, we also want to ensure that we have it plugged into a grounded power supply. Like all sophisticated electronics, the MX2 comes with a power supply designed to be used in industrial environments. Noise is particularly problematic in the TOF and phased array groups, so it's not a bad idea to use some type of verification of your ground power source and compare it to battery power or electrical power. It's the source of a lot of support. So again, it requires a clean electrical source. The MX2 is a fully functional touch screen that has several modes of operation. All functions of the instrument can be performed from the touch screen, the rotary knob, the increment keys, and the function keys on the left and right hand side of the instrument. These will control all menu and submenu navigation, zoom and pan features, gates, numerical input, parameter selection, and toggling between lists of readings that we'll see in the software shortly. Also included on the instrument is the online help index. For the relative section of the software you're viewing, selecting the help button will enable the online help menu, and we would encourage you to look at that and read through the material, as it answers a lot of questions that a typical customer wouldn't figure out by themselves without reading it or going through the training material. Again, selection of the help a second time brings the instrument back into the normal view. When we get to the instrument, we're going to see 3 modes of touchscreen operation. These limit what is possible to focus or manipulate on the touch screen at one time. The default is in zoom mode. While in zoom mode, both the gate and cursors have been disabled. Switching between the modes by touching that area of the display allows certain things to be enabled and other things to be disabled. Use of the touch screen and the MX2 requires a little practice and understanding of those modes of operation, and we'll see those when we're in the instrument. In the zoom mode, we have a zoom and a pan cursor. The function key associated with the zoom is the icon you see here. That's how we will zoom in and out quickly. Touching the zoom allows the pan where the display can be recentered in the area of interest. The user interface is divided up into 6 unique areas that contain different information. Each particular area is described in the full MX2 training program. Our data windows in the middle are the primary interest for the S-scan, A-scan, C-scan, and we will see a breakdown of the menus here and sub-menus here when we get to the instrumentation. The full version of this that's available in the download you'll receive explains each of these areas and their particular functionality. So again, in our last section in part 1, we talked about the theory and the ingredients that make up a phased array group or channel, typically a sector scan. Now, today, we're going to look on the instrument and use the various wizards to help develop the sector scan and understand a little bit about each one of those. So there's 3 parts to this. There's the part and weld wizard, the group wizard, and the focal law wizard. They all go hand in hand, and we're going to step through each section in the PowerPoint, and then I'm going to move to the instrument to explain each one in detail. So we start every setup with the part and the weld. Regardless of how many groups you're using, sector scans, ANTOFT, or different sector scans, The part is relative to all of the groups, and it contains the thickness, material, CSC mode, and the weld overlay if used. The thickness entered for the part is not relative to the focal laws or to the beam formation. It's strictly relative to the skip lines like B0 representing the bottom of the component and T1. These references are available in the A scan and in the S scan, and this thickness can be changed at any time. The velocity is an essential ingredient and the subject of much confusion for phased array. You either have to know the velocity of the wedge and component, or you have to measure it. We often call the velocity function a calibration, but in fact, you're not calibrating the instrument, it's digital. You're assigning a velocity so the displays will display the data in time correctly. So we normally select the velocity directly from the database. For us to be able to improve on what is selected from the database, it must be measured very, very accurately. Your ability to measure it on common blocks by peaking signals is very much in doubt over selecting the velocity from the database itself. And there'll be some more on this when we get to calibrations in the next section. The CSC mode is telling the instrument what is the geometry that we're looking at. The overwhelming majority of these inspections are plate geometry. Even if it's a pipe-to-pipe girth weld, it is still considered plate. The OD-ID versions of this are for an orientation and a COD wedge like you see here. They will correct the depth and surface distance readings based on the curvature of the component. And again, this is not changing the focal law calculator. It is just changing the correction in the readings similar to a digital instrument. Focal laws for this orientation must be imported from an external calculator. So we're going to pause right there and transition to the actual instrument and go through this first part of this together. So here we see the MX2 instrument. This button here we had mentioned is our main menu button. Upon selection, we will see all of the various menus available in the MX2. We developed the wizards so that it was not necessary to have to move to many different menu items to populate parameters for a basic setup. So selection of the menu wizard enables the part and weld, the setup, focal law, and the calibration. The PowerPoint that we just looked at discusses the part and the weld, and it should be a very quick function. Selection of start, enter the material thickness. Again, it has nothing to do with the component's beam formation. It's just the skip lines. We will select velocity from the database. And we will select plate for piping girth welds or for plate geometry, meaning that the ID and OD surface are parallel and not curved. We select next. When we get into weld inspection in a later section, we will also add the weld overlay. At this point, for just S-scan manipulation and verification of beam parameters, we will leave the weld off for now. So we've completed the part and weld, or part 1 of 3 of our basic setup, by assigning those parameters to the setup. Moving back to our PowerPoint, then part 2 of our setup is going to be the actual group formation. Every individual step is explained in great detail in the full MX2 training program that is included in the download material you will receive from this webinar. It takes us through a step-by-step of populating the hardware necessary to form our first sector scan group. So the group overview, there are 3 basic types of groups created with the MX2. A pure phased array group, like we're going to be using today, means that it's being generated from a probe that is connected to the phased array connector. Use of adapters with this connector will allow phased array and conventional UT to be performed during the same acquisition. Examples of that might be a TOPS group, transverse scanning for pulse echo probes, or conventional probes supplementing the phased array. So this option is for a UT conventional probe through this connector. And then with the addition of the new modules that allow simultaneous use of both the conventional LIMO connectors and the focal law, the phased array connector, are now available here. So we will select the phased array group. As we learned in section 1 of this, we will select the probe. Probes are normally automatically detected by the software. Where 2 probes are used instead of 1, it requires auto detect to be turned off with a splitter and selected from the database. The probe's essential parameters are the model, frequency, number of elements, size or pitch of the elements, a reference point, and if entered, a serial number. We will also select the wedge directly from the database. They're not automatically selected. During section 1, we talked about the essential parameters of the wedge. There are many entries in the database for different probes and wedges. It's very important to make sure you select the correct one. Historically, wedge problems account for the overwhelming majority of most of our support problems, and most of that comes from the wrong wedge selection. The probe position has nothing to do with the focal laws, but everything to do with the displaying of data correctly in the different views like the A-scan, S-scan, and C-scan. The orientation of the probe relative to the weld line or mechanical movement is what we call the mechanical skew. This is probe skew 90 in this orientation, and this is probe skew 270. And here we also see additional TOPS groups as well that would require a scan offset. The index offset is the position relative to the weld here to the face of the wedge. And in a manual inspection, we will leave this 0 until we find a flaw. And again, we are stepping through the wizard one step at a time, completing the necessary setups for the focal law of the sector scan. So we've completed at this point the group wizard, and we will go ahead and take a look at that on the instrument. So again, we select our wizard, and under our setup, we have the ability to either add or modify our current group. So in this case, we're going to modify the default group 1, and here were our 3 selections, either from the UT conventional LEMO connectors, UT through an adapter on the phased array connector, and here is the phased array mode. Select next. Auto detect is on, so we automatically just select the probe. The software knows the probe. We select the family of the probe wedge first, and then the associated wedge for that particular probe here, and the associated information is displayed. Select next. Okay, this is all scanner and probe position information. For a manual inspection, we will select, keep the defaults and select next. And we will have finished, at this point, the group setup. Taking us back to the PowerPoint. Upon completion of the group setup, the next part takes us to the focal law. And again, just to review, at this point, the instrument knows the velocity and thickness of the material. It knows all of the hardware, probe, and wedge associated with the group setup. And now we're ready to move to the software part of this, which is the focal law generation. 3 parts hardware: probe, wedge, material. 1 part software, which is the focal law beam formation. And again, the wizard here will take us through all of the various steps to where we generate the S-scan. So when we talk about the beam steering limits, at what point can we create an A-scan? Most of the probes and wedges used are designed for approximately a 30 to 75 degree shear wave beam. The software is not going to define the limits of where you can steer the beam. A N55S wedge generates a refracted 55 degree angle in carbon steel without any beam steering necessary. It's the natural Snell's angle. When you attempt to program beams outside the normal range of, say, a 80 degree shear wave or a 20 degree shear wave, what happens is the software doesn't give you an error message. The A-scan will be of such poor quality, it cannot be calibrated. That ultimately is how we determine the limits of any probe and wedge. The size of the elements in the probe are the main determining factor on how the beam can be steered beyond its natural angle. But again, a shear wave wedge at 55 degrees is typically calibrated between about 30 and 75, depending on the type of calibration reflector and use in the normal code calibration blocks. The software will need to define the first element start position of the beam. So in this case, we have a 64 element probe. Element 1 is here, and element 64 is here. So the position of the first element is going to determine the exit point in the wedge of the individual beam and the sector scan. So normally, in a weld inspection, we would exit the beam in the wedge as close to the weld as possible. So the first element position is also relative to the total element quantity. In this case, this probe has a 0.6 millimeter pitch probe. So if I use 16 of them times 0.6 millimeters is going to give me a probe aperture just short of 10 millimeters. The two parameters I'm seeing here are simulating a 10 millimeter by 7 millimeter conventional beam. And we can manipulate it with a beam tool plotter like you see here, or directly into the instrument. In this case, if we want the exit point on the wedge to be as close to the weld as possible, the last 16 elements in the probe would start with element 49. 64 would be the last element. So I'm using the same aperture, but moving it to the far side of the probe. And this is programmable directly into the software. Now, what is the benefit of using a 16-element instrument over a 32-element instrument? The power of the pulsars, this is called. Given the same aperture or the same size probe, the more individual elements that are placed inside the aperture give us better beam quality. Okay, by beam quality, we mean signal to noise ratio. Okay, this is a crack tip for an L-wave inspection that was detected and raised to 80% amplitude. So when we look at the tip of the crack at 80% amplitude, we can see a little bit of noise here. This is the shear wave mode converted signal, always present in the L wave, and some more noise here. This is using 27 elements times 0.6 for a 16 millimeter aperture. Okay, so if we take the same size aperture here, but we used a 16 pulsar instrument and a larger pitch probe, so we end up with the same aperture or same probe size, but our beam quality is very different. Our ability to focus and generate as much energy as possible directly out the crack tip. In this case, the crack tip is detected at a much lower amplitude. If we raise the gain to make this 80%, we will also see the associated noise being raised, making it very difficult to identify the crack tip. So more is better in this case, and more power. But the overwhelming majority of most of our applications are being performed with 16-element pulsars. Okay, the beam min-max angle is entered along with an angle step resolution and a focus depth. We'll see the start angle here at 45 degrees and the maximum angle at 70 degrees. My ability to calibrate each A-scan to verify horizontal and amplitude linearity and an overall good beam signal is what determines the limits of how far or how wide. For instance, an ASME Section 8 calibration block would use a different side drilled hole for a 12 millimeter vessel than it would for a 100 millimeter vessel. The size of that hole and our ability to calibrate each beam will very much determine the maximum angular range of what we can use. The step resolution that we see in this example, we're using a 1 angle step resolution. Here, we can see that any potential flaw is being detected by several different beams. Depending on the frequency of each beam, these beams are also overlapped significantly. The sector scan display that we see of a 1 degree resolution compared to a 1/2 degree resolution is very different. The more A scans we use in the sector scan, the better our sizing or characterization. When the resolution is smaller, the file size is increased, and the scanner speed must be slowed down. In lots of our applications, it's not the bottleneck or significant, but we can see here with more A scans, we're going to have a much higher resolution and a better inspection if it doesn't cause us file size or scanner speed problems. Again, more is better. To give you an example of an application of why we would use a different angle step, we're looking at a 100mm weld here and 4 sector scan groups that are inspecting it. The bottom sector scan groups are traveling on the first leg to the weld, a short distance. So they're using a 1 degree step resolution. The upper coverage is bouncing off of the bottom of the vessel and inspecting on the second skip. So it has a longer time of flight and greater beam divergence between every 2 A scans. So we improve the inspection on the second leg by using a 1/2 step resolution for the sector scan. This is combined with 4 Toft groups that are covering the range in different zones and a merged C-scan that shows us the sum of all of the sector scans. This is OmniScan data that was converted to TomoView, or an offline analysis program where we can combine and customize the displays. So again, our ability to identify the center of the energy of a defect is what defines our ability to resolve its depth. So the depth and height is greatly improved by using a higher angle step resolution. Better data, more information, better ability to see tips and peaks and characterization that separates a linear flaw like lack of fusion from a volumetric flaw like porosity or slag. Our focus depth, for the majority of our inspections, our focus depth comes for a code-based reject criteria that's designed to be used with a conventional unfocused probe. Entering in a focus depth greater than the near field of the probe amounts to basically an unfocused probe. Entering a number within the near field of the probe allows a focal plane to be created in this axis. Focal planes other than depth, such as half path, projection, or XY or focal plane defined in the material, require use of an external calculator to import the focal laws. The OmniScan built-in calculator is limited to depth. And an example of why we would use some other type of in-focus strategy, here we have an Inconel weld with an Inconel clad layer and a carbon steel base material, and from the probe exit position, we're focusing directly on the far side weld bevel in several passes. So our results are improved significantly by changing the focal plane in these type of inspections. This focal depth is limited to the mathematical near field of the probe and wedge, which is available in the NDT-S setup builder or typical beam plotters like the ES beam tool as well. The beam exit and beam angle, how do you know if what you are asking from the software is really what is reflected in the material that you're inspecting? How do we verify the beam parameters for what we're asking for and what we're getting from the instrument and software? And the answer is exactly like conventional UT. For any A scan within the sector scan, I can verify first the exit point of the beam using the same typical IIW block as conventional UT. And once I verify that the exit point matches the software, I can flip the block over and I can verify that the angle is really represented in what the software is, plus or minus about 1 degree is normal. This is the same function as conventional UT, and there are procedures for this in the MX2 training program that are included in the download of the material for this webinar. And again, use of standard procedures like the 2491 that allows a series of common calibration blocks to define the angle limits of any given scan plan is another way that some customers require those beam parameters to be verified. So we're going to transition back to the instrument again and complete our setup. So at this point in the software, we completed the setup wizard, and now we have an opportunity to continue to the focal law setup here, which would be the same thing as the focal law setup here. We select continue, and we can ask for either a sectorial or linear scan. And for the ray tracing, either 1 or 2 legs to be seen in the plotter. Select next. The material was locked when we selected carbon steel during the part and weld. It associated 2 velocities from the database based on mild steel. Now I can enter in a known velocity. I can calibrate or measure the velocity using the calibration block and the calibration velocity wizard. More than likely for carbon steel, we're going to be better off using the database velocity because your ability to measure it within 25 or 50 meters per second is very much suspect depending on the type of probe and calibration block you're using. We select next. Again, we have our 1 and 16 element parameters from the probe. When we look at a beam plotter like this, we are seeing here element 1 of a 16 element aperture. Here is probe element 1, probe element 16, and we have a 55-degree refracted angle being generated into the material. Obviously, if I start the element at a higher position, it's in a better position for the inspection. This is a static single focal law, and here we will see the full sector scan. 16 element aperture, or simulating a 10 millimeter conventional probe, starting on element 32. So select probe first element and element quantity. And again, this is also limited by the instrument as well. A 16-128 instrument would not allow a quantity greater than 16 to be entered here. Select next. Enter our angular range angle step and focus distance that we had just spoke about. And just moving back one step, to give you another example of the difference of a 16 or 32 element. Okay. What we're looking at here is a data file of a 1 millimeter by 10 millimeter notch in carbon steel. Here. This is a sector scan looking at a 1 millimeter notch, and we're looking at the tip diffracted signal from the tip of the notch here. With a 16 menu focal law aperture, a 16 element aperture focused at the depth and a 1 degree step, we can see our ability to measure the center of this tip is compromised. It's fairly broad and fuzzy. This is one corner of the notch, and this is the other corner of the notch. So if we were to do the same inspection using another group here, this is a 16 element aperture, and this is a 32 element aperture at a higher focus. So our ability to measure the depth of the tip and the width of the tip is very different. And again, here is the 32 element instrument versus the 16 element instrument, combining focusing, more energy within the same aperture, less beam spread, and better characterization and sizing. So we select the element quantity, select next, our angular range from 45 to 70 at a half degree step in this case, and we'll focus right at our side drilled hole. Oops. Select next. Okay, we have the opportunity in the wizard to enter in our gate position as well. We're going to talk a little bit about C-scan and gate position in section 3. So just accept the defaults and generate. So we've created our sector scan group using the 3 parts of the wizard setup. We'll go back to the PowerPoint for a moment. So after the basic phased array setup, we're going to do a little UT configuration and then look at manipulating the S-scan. So our function keys start to come in very handy once we've got our sector scan and we're manipulating it. The DB function key automatically takes the user to the UT gain menu, and the user should familiarize yourself with all of the function keys. Expert usage and no mouse manipulation of data and cursors is greatly enhanced by knowledge of and a little bit of practice using the function keys. When we set the range is set based on the current A-scan we see in front of us. As I change the blue cursor, I will see a different range for every A-scan, but they're configured as a group. The UT range is also available in a series of function keys that takes you directly to the UT range parameters so they can be manipulated without having to actually navigate the menu. Under the pulsar of the UT settings, we're going to select either a high or low energy depending on the size of the elements and best results. We'll select a frequency for the bandpass filter. If you receive your probes from the factory, you should take a look at the frequency bandwidth. Here we see basically a 5 megahertz center frequency of a broadband probe. In this particular filter, we're going to see crops from about 2.5 or 3 megahertz to about 7.5 or 8 megahertz. So we're using the most useful range of the probe, and a no filter would be using the entire bandwidth. Select the video filter. Video filter is a type of digital smoothing that allows us to more easily identify the center of energy or our location for a measurement. And our beam parameters that we'll talk about directly on the instrument. So I'm going to skip over this quickly. And our point quantity. Points are very relative to phased array inspection because they're related to file size and speed, but they also allow us to determine the type of resolution we want on the A scan. All phased array instruments use a type of compression that would allow you to never miss amplitude data, but compress A scan resolution by fewer points so that you can generate more data or have a smaller data file or faster scan speed. And then that would get us to the S-scan overview. So we're going to go back to the instrument and configure the rest of the UT settings. So we have completed the wizard options, and we move to the UT settings, which is very similar to a conventional digital flaw detector. We're going to enter in the range we see here. The velocity was determined from the component during the wizard for carbon steel. Under our pulsar, we can normally just set it to optimum. Select one of 3 energies based on the pitch of the probe and best results. Select the filter. And our beam settings that you see here were generated by the phased array calculator. When we look at the beam information, the delay here was automatically calculated for every focal law. Our index offset is the exit point. If I measured this on an IIW block, the exit point should be exactly the same as what the software tells me it is. If the exit point and the angle are verified on the IIW block, I know that the A-scan is within the range of the probe and weld and target that I'm looking at. So in the instrument now, we have a single group of a 16-element aperture. So to manipulate the S-scan, we're going to use a series of function keys and or menu items. Select function key data cursor, shows me the angle and allows me to manipulate the data cursor here. I want to pay particular attention to the size and shape. And I'm looking at now a 5 millimeter or a 1.5 millimeter side drilled hole in a standard IIW block. So my focus, my frequency, the probe aperture is all relative to the quality of the signal. Again, here is a 16-element aperture. I can see that it's being detected by multiple A-scans because of the beam spread. function key, angle, and I can go full screen and change to group 2, which is a 32 element aperture of the same probe. So we can see the detectability, the size and shape of that 15 millimeter deep hole is of very good quality. Now, prior to any calculation, prior to any calibration, we're coming directly out of the focal law calculator. We can see that the depth of the side drilled hole is correct. If we change under display to view settings, selection, highest amplitude, the software will automatically track the signal in the gate. So now, as I move the probe back and forth on the calibration block, within my red gate, the software is looking for the maximum signal amplitude and automatically adjusting the A-scan. If you can maintain the signal at the correct depth, and in this case it's 15 millimeters, across the entire sector scan prior to calibration, this right away is an indication that the velocity of the wedge, the velocity of the component, the probe and wedge parameters such as pitch, height, wedge velocity, wedge angle, it's an indication that all of those are correct. It is impossible to arrive at that sector scan with that target at the correct depth across the whole sector scan if all of those parameters are not correct. So we have several functions available to us for either displaying the current law with a sector scan and A-scan, or all laws, which is an A-scan merge of the sector scan data. We use the function key here to manipulate the S-scan with the rotary knob, and this will switch between the angle and the S-scan or the scan axis cursor of the C-scan on a short and long stroke of this function key. And the manipulation of the A-scan. In the end, upon successful completion of the setup and verification using standard calibration blocks, ultimately we want to be able to verify that our beam is of the same quality, linearity, and accuracy of conventional UT. And we can see here that in the phased array sector scan using the wedge delay calibrator that we're going to learn in the upcoming section, and using a series of checks that we've already discussed for every individual A-scan, and in this case the 55 degree, we have accurate sound path, wedge delay, velocity, and linearity across the whole array. In this example, we took just a small clock scan. I start here I start the clock, I take a small scan of the cow block exposing every focal law to this position, which is the 50 millimeter and 100 millimeter position, so that any A-scan basically meets the beam quality and calibration of an ASME Section 5, Article 4 calibration. When that can be done, then it's easy to use phased array in our conventional procedures or development of our applications expanding on what conventional UT is doing. So again, all of the presentations that you saw, the sample data files, and the non-abridged version of the training PowerPoints will be distributed to you guys in a download. Be sure and email the phased array support any questions you might have regarding this webinar or an earlier one. And we saw some questions and answers during the course of the presentation that we will send everybody in a follow-up email. So we've used up our time for today. Next session, we're going to get into calibrations and defect sizing. Thank you, everybody, for attending. I'm going to turn it back over to our moderator, Greg, and I'll see you next time. Thank you very much.
Thanks, Chris. Nice job. On behalf of Olympus, I'd like to thank Chris Magruder for his participation in this event. Thanks very much to all the attendees for joining us. We hope this material presented was informative and useful. This webinar, along with Q&A, will be archived on our website at www.olympus-ims.com. Follow-up emails will go out to all attendees with links to all the files used in today's presentations, as Chris alluded to. Part 3 of this introduction series will be on March 21st at 11 a.m. Be sure to sign up on the website for the next part of this series. That's going to do it for today, and again, thanks to everyone for participating, and we'll see you on March 21st.